Hello everyone, welcome back to my channel. In this video, you will learn the essential steps in designing a rectangular combined footing, including the following key points when to use the combined footing. And the second is how to determine the appropriate size of the combined footing based on loadings and soil condition. The third one is how to evaluate both one-way and two-way shear to ensure structural safety. And the fourth one, how to calculate the required longitudinal and transverse reinforcement, including the temperature and shrinkage reinforcement. And the fifth one is we will discuss the common site mistakes in footing design and reinforcement detailings on how to avoid them. So we will reflect all the reinforcement that we have calculated into the plan so that you can figure out how it looks like in the actual project. So stick around guys, because this video is a little bit longer. Now let's get started with our problems. But before we proceed guys, let me explain quickly regarding when to use this combined footing. So basically, combined footing support more than one columns. And one situation in which they may be used is when the columns are so close together that isolated individual footings would run into each other, so very close, as you can see here in our sketch. And the other one, the most common problem is the overlapping of isolated footing or clashing between foundations, where the combined footing is the appropriate one to choose. So back to our problem. Design a rectangular combined footing for the two columns shown in figure below. Given an allowable soil bearing pressure of 4,000 psf, yield strength of steel is 60,000 psi, concrete strength is 4,000 psi, and the unit weight of soil is 100 pcf. Assuming the top of the footing is limited to 3 feet below grade. So this is our elevation of the combined footing. We have the 3 feet below the grade, and column B, 12 inches by 12 inches. We have the 135 kips dead load and 100 kips live load. So in column A, 16 inches by 16 inches column with dead load of 200 kips and 130 kips live load. So step-by-step solution guys. First, we need to calculate the total service load. So for column A, we have 200 plus 130, that is equal to 330 kips. So that is the total load for column A. For column B, 135 plus 100 live load is equal to 235 kips. Now the total load for the foundation is the summation of column A and B, which is 330 plus 235 kips, that is equal to 565 kips. So that is the total load of the combined footing. Now we are going to locate the resultant load. So we have the resultant here, reference from column A. So to locate the resultant load, we have X times the load from column B times 15. The distance between A and B is 15 feet over 565, that is the total load, is equal to 6.25 feet. That's why the location of our resultant load is 6.25 feet from the center line of the column A. So the center of the footing must be 6.25 feet from the column A. So remember guys that the resultant of our load is also coincide with the center line of our foundation in order to achieve the uniform soil bearing pressure at the base of the footing. Now we will determine the footing size. So assuming the total depth of our footing is equal to 28 inches. So let's clear cover to the centroid of our steel bars. So let's say 4.5, 28 minus 4.5 equal to 24.5 inches, and that is our estimated effective depth of footing. Now we can calculate the effective soil bearing pressure, meaning we have to deduct the foundation and the overburden soil. So 4,000 PSF minus 28 inches, that is the depth of footing, times 150 PCF, minus the 3 feet, the overburden soil, times 100 PCF, unit weight of soil, that is equal to 3,350 PSF or 3.35 KSF. Now we have already determined the net soil bearing pressure, so then we can calculate the required area of the footing. So 565, the total weight of the columns, over 3.35, and that would give us 168.7 square feet, and that is the required area of our footing. So let us assume that the length of footing from here to there is 20 feet. So we will assume 20 feet length of foundation. So remember that the length of our foundation, the center line of our foundation, is the location of our resultant load in order to achieve the uniform soil bearing pressure. So the half of 20 feet is 10 feet from here. So if we have 6.25 from column A, the location of our resultant, meaning 10 minus 6.25 feet, that's why we have 3.75 feet. Now, we will estimate the width of the footing. So 168.7 over 20 feet is equal to 8.44 feet. Let's say the width of the footing is 8.5 feet. So we will adapt the size of 20 feet by 8.5 feet of footing, so that give us the area of 170 square feet. So that is the size of our footing. Then we can proceed to determine the factored soil bearing pressure and factored load for column A and B. So the factored soil bearing pressure, based on the this is based on the loadings, column load. So we have 1.2 times 335 kips. This is the total dead load of the columns, plus 1.6 times 230 kips, total live load over 170, that is equal to 4.53. So we have the factored soil bearing pressure. So we have to calculate also the factored column load. So at column A, we have 1.2 times 200 kips plus 1.6, 130 kips, and that would give us 448 kips for column load. That is the factored column load. So for column B, we have 1.2 times 135 dead load plus 1.6 times 100 live load. That is equal to 322 kips. That's why we have 322 kips here. Then we can now proceed to draw the shear and moment diagram. So first of all, before we draw the shear and moment diagram, we need to calculate the uniform distributed load. So 4.53, which is this one, this is the factored soil bearing pressure. times the width of the footing, 8.5. So we have 38.51 kips per foot. This is the uniform pressure here at the base of footing. So we convert it to uniform just like we apply loads on the beams, so that we can draw the shear and moment diagram. Now we have to, first we have to find the shear at point 1, at this point. What is the shear at this point? So we have here 118, that is 3.08 times the uniform load, which is 38.51. That would give us 118.6 kips at this point. That is the shear. So at this point, this load 150, that is V2, so 118.6 plus 1.33 feet, because this is 1.33 feet, times the uniform load of 38.51 minus 448. This is very important. Minus 4.8 down, this was the pressure from the column load. So that is equal to negative 278.2. This is how we come up this problem figure, minus 278.2. So now the next one is to determine the shear at this point. What is the shear at this point? So that is V3. So V3 is equal to negative 278.2 plus the upward load here, upward uniform load, which is 13.83 times 38.51. That is from here to there is 13.83. So multiply that one, that would give us 254.4. So that's why we have here 254. The shear is linear because our load here is uniform. So if load here is uniform, this is linear. Okay. So at this point, shear at 4, that is 254.4 minus, plus the upward soil bearing pressure of 1 foot times 38.51, this one here, minus 322. So you have to deduct that 322. That's why we have the negative 29.1 kips here. So this is the calculation for shear at point 4, negative 29.4 here. Now, the next one is to draw the moment diagram. So we have here the positive shear. So our moment is sloping up. The slope is positive because positive shear. Then at this point where we have the shear is 0, the slope here at the moment diagram is 0. So this is the maximum moment located at 0 shear. So the maximum moment here is equal to the positive area of the shear. So that is positive area of the shear. What is the area here is 1/2 times the length. The length here is 3.08 plus 0.4, and that is equal to 3.48 times the height. That is the load 118.4, and that will give us moment of 206.4 here. So that is the moment at this point. Then the next one is to find the maximum moment here at this point where we have the 0 shear. So to calculate the moment at this point is just the summation of this area. So this area here positive area minus the negative area, that is the moment at this point. So what is that moment? The moment here is 206.4 minus this area here, negative 0.5 times 8.15. 8.15 is from here to there, that is 8.15. 0.93 plus 7.22 feet times the shear at this point, 278.2, that would give us negative 927.3. So that is the maximum moment at this point where we have the zero shear. Then the moment at this point where we have the zero shear at this point here is very small, which is only 28. So you can add this positive area here, positive shear area, minus the negative shear area here, plus the positive area here. Is very long. So the shortcut here is 927.3 plus this area, and that would give us 28 feet. So here, see, minus 927.3 plus 0.5 times 7.51 times 254.4, which is this one, and that would give us a 28 feet. So that is the moment area here. So the next one is to check the depth of footing for one-way shear, or what we call punching shear. So we have already determined the maximum moment. Now we are ready to check this reinforcement. And when we check the one-way shear, we have to use this maximum shear, which is the maximum shear, which is 278 at this point, because the load here is very high compared to column B. So to check for one-way shear, the maximum shear is 278.2, which is this one, 278.2. Now, what is the shear at the distance D? To calculate this distance D, you have two options. Either you can use this by ratio and proportion, or you can use this by summing up forces here, which is this one, 278.2 kips minus 24.5 over 12, that is the D, distance D, times 38.51, that is the uniform load from here, that's the uniform load, is equal to 199.6 kips. So this is your design shear at this point here, that is the one-way shear. We will check that based on the equation given by ACI section 22.5.5.1. So the width is to be considered is 8.5 feet, which is equal to 102 inches. So the depth is equal to 199. So we'll just convert that into pounds. 99,600 pounds times 0.75. The fee here is 0.75 times 2 times the square root of 4,000 times the width is 102, and that will give us 20.63. So the total height based on this requirement is the depth plus 3.5 is equal to 24.13. So let's say we'll use 26. So this is the actual depth that we are going to use based on this requirement, to satisfy these requirements of one-way shear. So the next one is to check for punching shear. So to check this punching shear, so we have here the equation given by section 9.6 0.1, 0.2. And first we need to determine the perimeter area. The perimeter length is equal to depth plus the width of the columns, which is 38.5 is equal to 3.25 feet. So we just express that into feet. So here the V2 is equal to 448 kips, which is the load from the columns, minus the area. The area here is 4.53. Now this is the soil bearing pressure, the factor soil bearing pressure, 4.53 kS times 3.21, that is the punching area here. The punching area is 3.21, is equal to 401.3 kips. So that is the punching shear. So the depth, plugging all this value to this equation here, we have 300 pounds over 0.75 times 4 times the lambda. Lambda here is 1 because we are using the normal weight concrete, times the square root of 4,000 concrete times 154 is equal to 13.73 inches. That is the required depth for punching, which is less than to 22.5. So our depth assumption is correct. So we are okay. Now there is another one equation from ACI section 22.65. We have this equation V sub U2 P times ED over BO plus 2 times lambda square root of FC prime times BO. So A here is equal to 40 for interior columns. So this one we can consider it as an interior columns where the perimeter is four-sided. So if it is on the edge, so we have three-sided columns. So we have different value of A. Now plugging all this value of this parameter here, we have 300 pounds all over 0.75. So 40 times the depth, but here over 154 inch plus 2. So times the square root of concrete, 4,000 times the perimeter of the punching area. So the perimeter we have calculated that previously here, 154, and that will give us 7 inches, which is less than 22.5. So it's very small. Normally other engineers do not calculate because it will not go burn. So that for our discussion purposes, we just include this one. So that is okay. So the next one is to design the longitudinal steel. So here we can calculate the reinforcing bar at the bottom based on the maximum moment of the foundation. So from the moment diagram, the maximum moment is 927.3 kPa. So here we have is the basic equation from the flexural formula. We have this general equation just like in the beam. So M, we need to calculate these two parameters M and Rn in order to calculate the steel ratio by giving this formula here. So M is equal to Fy over 0.85 Fc prime is equal to 60,000 psi over 0.85 times 4,000 psi, that is equal to 17.65. So using the B.5 feet, which is also 102 inches, and the depth of 22.5, we can calculate the Rn, this one. So Rn is equal to 927.5 times 12 times 1000 over 0.75 times 102 inches times 22.5, and that would give us 287.32. And this is, by the way, this is 22.5 square. So Rn, we have calculated M. Now we can substitute to this equation. Then we have this one, 117.65 times 1 minus 2m Rn, then divide by Fy, 60,000 psi. That will give us a still ratio of 0.00501. So area is equal to rho BD. So that is equal to 0.00501 times 102, the width of the footing, times the depth, 22.5. So the required tension reinforcement is equal to 11.5 square inch. Now, if we use number 8 bars, we need 15 pieces. And that is equal to 15 pieces, diameter of 1 inches, 11.79 square inch, which is greater to the 11.5, the required area. So our 15 number 8 bar is okay. Now the next one is the top bars. The top bars, based on our moment diagram, we have the 206.4. That is under the column loads. So the moment 206.4 keeps fit. So we will calculate the reinforcement, and we will substitute that all the parameters from this equation here. As what we did previously, we have to calculate M and Rn. So we have the 60,000 psi, 0.85 times 4,000, so 1765. So the same width we'll use. Then moment is 206.4 kips fit times 12 times 1000 over 75 times 102 times 22.5 square. That will give us 64. So substituting to all this figure to this formula, we'll have this one here. And that is 1 minus square root of 1 minus 2m Rn over Fy. So 64 over 60,000 psi, that would give us 0.00106. So by inspection, this is less than to the minimum requirements. So we will check the minimum requirements as per the ACI section 9.6.1.2, which is 3 times the square root of Fc prime over Fy is equal to 3 times the square root of 4,000 over 60,000 psi. That will give us 0.00316, and that is the minimum. So the other provision is 200 over Fy. 200 over 60,000 psi, the strength of steel, that would give us 0.033. So this governing one, the minimum will govern for the reinforcement at the top. So rho BD is equal to 0.0033 times 102 times 22.5. That would give us 7.6 square inch. So if we use number 7 bar, that would require us to use 13 pieces, which is a total area of 7.81 square inch, which is greater than 7.6, the required area, this one here. Now the next one is to design the reinforcement in a short direction, or transverse reinforcement, and that is the bottom reinforcement there. So the maximum moment at the bottom, which is here, we need to calculate the lever arms, which is 8.5 minus 1.33 feet over 2. That will give us 3.58 feet. So the design moment in short direction is calculated. Mu is equal to 52.71. 52.71, that is come from 444, the total load of the columns, divided by the weight of the footing, which is 8.5, the weight of the footing. That would give us 52.71 kips per foot. That is the uniform soil bearing pressure. So 52.71 times 3.58 square over 2, that will give us 338 kips foot. So that is the moment at the face of the column here. So we have calculated the moments. So the next one is to determine the reinforcement, giving the depth of 26 minus 3.1.3 is equal to 21.5. By the way, guys, sometimes this is confusing because if you are not be careful to determine the depth is in the second layer. That is the location of our transverse reinforcement. This is the longitudinal reinforcement, which is the main reinforcement. That's why it is placed always at the bottom. Now, the depth to be considered is 21.5. So, based on the second layer, placement of rebars. So, assuming the steel spread over the width B, which is the column width plus 2 times the depth over 2, is equal to 16 plus 21.5. So, if we look at here, this is the column width. Then we have the width of D over 2 here. So that is the width of our transverse reinforcement, the width to be considered for the design. So MY, we have 60,000 PSI. We have the same value, 0.85 times 4,000, 17.65. And the Rn is equal to 338 kips foot times 12 times 1,000 over 0.75 times 37.5, this one here, times the depth, 21.5 square, that is equal to 312. So substituting all this value here in this equation, that would give us the value of, that's why I'm mentioning this one, guy. I'm mentioning all this value just to double check also. So 312, this one, over 60,000 PSI. Okay, so the steel ratio is 0.00546. So this is the actual steel ratio required. So the minimum, this is actually greater than the minimum, which is 0.0033. So the required area is rho BD 0.00546 times 37.5 times 21.5 inches is equal to 4.4 square inch, and that is the required area in the transverse directions, bottom bars. So that is here. So now, if we use number 7 bars, it requires 8 pieces. And that would give us the total area of 4.81 square inch, which is greater than 4.4. So the next one is the temperature and shrinkage reinforcement. In most cases, some other contractor, they don't provide this temperature and shrinkage reinforcement. But most of the project, particularly if the drawing is reviewed by the third party. That is the most common comments, that the temperature and shrinkage reinforcements needs to be considered in the design. So that is as per the ACI 318 section 24.4.3. Minimum steel ratio, we have 0.0018 using the deformed bars grade 60, and that is the required steel ratio. Now the ES is equal to 0.0018 times the gross area. The gross area, that is the width times the depth of footing, 26 times 102 the width of the footings. That would give us 4.77 square inch. So using number 5 bars, and the area of bar area of number 5 is 0.31, we will express this into spacing. So the spacing is equal to 102 over 4.75 divided by 0.31, and that would give us the spacing of number 5 at 6 inches on centers. Actually, the spacing is 6.63. You can use also 6.5. Some other contractor, they prefer to use a whole number because it's very difficult to calculate 6.5. So top bars, short and longitudinal direction. By the way, guys, the temperature and shrinkage reinforcement is always perpendicular to the main reinforcement. So at this point, at the middle here, we will use the top and bottom, that is short and longitudinal direction. So this is our plan of the combined footing. We have here the number 8 pieces, number 7. This is a general, basic arrangement of reinforcement. So number 5, number 6, bottom reinforcement here. Then from here to there, we'll use number 5, 6, number 6 at 6 inches on centers, top and bottoms. So you will find here number 15 bars, required rebars according to our calculation, the required reinforcement. So this is the end of our calculation guide. Don't forget to like and subscribe so that you will be updated for the next upload. Thank you very much. See you next time. Bye-bye.